class we talked about LeChatelier's principle. LeChatelier's principle is used when there is a stress. We call it a stress on a system. A stress on a system upsets the equilibrium of the system, kind of like stress in your life may upset the equilibrium you have going in your life. So when you have a stress on a system, the system will react in a certain way in order to alleviate that stress. And so the first part we're going to talk about is when you start changing the concentrations. Remember, equilibrium was when the reaction's going back and forth at equal rates. And so it gets to like its happy spot, happy molarities, and so it always equals the K constant. So if you were to increase, maybe pump in something, we've got the Haber process going on here. If you were to increase the concentration, maybe we're going to put some more of this into our system. We're going to increase the N2. When you increase the N2, well, the reaction doesn't like that, so it needs to get rid of that N2. So the only way it can get rid of the N2 would react more with H2, and so therefore if you increase the N2, we say this shifts the reaction to the right. We call it a shift right. When it shifts to the right, you're going to be making more ammonia, and you'll be losing H2 because this H2 will be reacting with the N2. So if I were to increase N2, it's going to react with H2, so H2 is going to go down, and NH3 is going to increase because we're shifting right, we would say. And so the opposite of that, well, not necessarily the opposite, but if we were to increase this guy, increasing the H2, same thing is going to happen. If I were to increase this, it doesn't like that, so in order to make it get back to equilibrium, it's going to need to get rid of this. The way it gets rid of the H2 is by reacting with the N2. So again, this is going to shift. Helps if I could spell shift. This is going to shift again to the right, and so the NH3 is going to increase and the N2 is going to decrease. So that's really all LeChatelier's is talking about shifting based on some sort of stress. If I were to increase the NH3, then if this were to go up, then it doesn't like that. So what's going to happen is it's going to start breaking down. This is going to cause the shift to go to the left. We call it shifting left. When it shifts left, the H2 and the N2 are actually going to go up in concentration. So if you shift to the left, your reactants go up. If you shift to the right, your products go up. The only thing that's going to affect the K, though, is temperature. So these things are going to shift, they're going to get back to their equilibrium state, and then the K will stay the same. So the only thing that affects the K is a temperature change. Now if we talk about removing, if I were to take some of this and remove some of this from the system, maybe remove all of it, remove the N2 from the system, well, it needs to replenish that, so therefore this is going to cause it to shift to the left. That means that the NH3 would break down, H2 would go up, and we would also get some N2 going up as well. The NH3 would go down. So it shifts towards the removal and away from the addition. And so if I were to remove this guy, again, it's going to shift to the left, and N2 is going to go up, and NH3 is going to decrease. K is again going to stay the same. And then if I were to remove this guy, then the N2 and the H2 was going to keep it reacting together, and we're going to make some more ammonia. And I told them in class, this is what happens in the Haber process. In order to keep that reaction going, they actually remove some of the NH3 to keep the N2 and the H2 reacting, for they won't get to a stable source of equilibrium. Alright, the next thing we talked about was whether or not a reaction was endothermic or exothermic. And there's two ways to illustrate whether a reaction is endothermic or exothermic. I'm going to go to a separate page, and then I'll come back to this one. If you had a reaction, we're going to say A plus B, we'll just say makes C. There's one way we could illustrate this. We could have delta H for this reaction equals a positive 12, we'll just say kilojoules. So this reaction, this is sitting over to the side, it says positive. That means that this is an endothermic reaction. We did the graphing before, and we said that if your delta H is positive, it means it started out high and went low. If we think about those graphs, it's a really bad graph there. that that is an endothermic reaction. You end up with more energy than you started with. This is one way to illustrate an endothermic. Another way to illustrate an endothermic would to actually be put it into the reaction. And so if we put it into the reaction, it's endo, so endo is part of the reactants. We would put this energy right here. So this is two ways to illustrate an endothermic reaction. An exothermic will go with the same reaction here. Would be if it's over to the side, we would see a negative value. We'll say negative 520 kilojoules. This is one way to illustrate it. If it's negative, it's exothermic. Another way to illustrate it would be to put it as part of the reaction. Notice when I write it in the reaction, it's always plus. But what side did I put it on? This time I put it on the product side. So when the kilojoules is on the product side, it's exothermic. That's reading the equation from left to right, the reactants and the products. If it's part of the products, then A plus B making C is an actual exothermic reaction. If it's over here on the reactant side, then it's going to be an endothermic reaction. And the reason you want to do this is if you have it written like this, you're going to want to write it like this, because if you write it into the equation, then you can just treat it as if it's one of those reactants or products. So we're going to go to this equation, and I forgot the value, but I think on the sheet it says it's a negative, it's a negative 9.6 joules. I could be completely wrong on that, but we'll just say negative. So would this be endothermic or exothermic? Hopefully you are saying this is exothermic because it's negative. So if I were going to write it into the equation, I would put it on the reactant side or the product side. You would put it on the product side because the heat is being given out, so I'm going to put it right here. So, now that it's part of the equation, I could say, well, if I were to increase the temperature, increasing the temperature would give it more energy. So if I increase the temperature here, it would be like increasing this, increasing the energy. And a while ago when we said if we increase this, it's going to cause it to shift to the left. Well, if I increase this, it's also going to cause it to shift to the left. When it shifts to the left, you're going to get more H2 and more N2 and less NH3 going on. So this is going to cause a shift to the left. And when it goes to the left, H2, N2 will both go up, NH3 will go down. And if you think about it, now it's making more of the reactants. Your K is actually going to change, and this is such a significant change, not like the other. It can't get back to the equilibrium like the other. Temperature really affects the constant. That's the only thing that really causes an effect in the constant is the temperature. This is going to cause, I didn't mean to put equals there, it's going to cause your constant to actually decrease. And the reason is, remember, the smaller the K, the more the reactants are favored. But if you think about it, it's products on top over the reactants. And if this is getting smaller and this is getting larger, then the K would be going down. So anytime it shifts to the reactant side, the K will decrease because your product is actually decreasing when temperature is involved. That is only when temperature is involved. Temperatures are not involved, K is going to remain the same. And the last thing that we didn't get to talk about in class, but we will pick up next time, but I'm going to go ahead and tape it on Edmodo for it'll be there. When you deal with pressures, you only care about gases. Gas is the only thing that matters. If you were to increase the pressure, now you could do that several ways, and one would be, if you think about Boyle's law, when the volume goes down, the pressure goes up. So when pressure goes up, volume goes down, and when pressure goes down, volume goes up. They're inversely proportional. This is called Boyle's law that had this to do with this. Well, volume is the amount of space. So if you increase the pressure, you're pressurizing these gases. And so it's going to favor the sign that would alleviate this pressure, because it doesn't like increased pressure. So, and what's going to cause that pressure is having more moles of gases. So if you increase the pressure, it's going to favor the side that has it's going to favor the side that's going to have less moles of gases. Because the side that has less moles of gases is going to have less pressure. And that should make sense. The more gas you have, the more pressure you're going to have. So if you increase the pressure, it's going to go to the side that has less moles of gases. If we look at this side has 4, this side has 2. So if I increase the pressure on this particular one, it's going to cause it to shift to the right. Conversely, if I decrease the pressure, it's going to go to the side that has more moles of gases. Almost made a boo-boo, almost put 2 S's on gases. So if I decrease the pressure, it's going to go to the side that has 4. Okay, so increased pressure, because it's so pressurized, it wants to go to the side that has less moles. And then if you decrease the pressure, it actually goes to the side that has more moles. If you want to think of it as this, if pressure goes up, volume goes down, and volume is space. If you think about space, if you get more pressure, it's got less space to deal with, and less space to deal with would be less moles. And as pressure goes down, you've got more space to deal with. If you got more space to deal with, you can actually make more moles. So you could also look at it in terms of volume. If the volume were decreased, that's an E, you're going to go to the side that has less moles. And it's only gases you look at. Remember when we did the delta N, it was only gases. When you're dealing with pressure and volume, it's only gases that we deal with. And then volume were increased, you'll go to the side with more moles of gases. And again, solids have no effect, so if something's a solid, putting a solid in has no effect. Doing these has no effect on the K. And then the last bit is a catalyst. Putting a catalyst in gets the reaction to equilibrium faster, but it has no effect on the equilibrium. It gets there faster, but it just still gets to equilibrium, and so we say that it causes no shift. The catalyst causes no shift. So it doesn't change the K, it doesn't shift the equilibrium. All it does is get us to equilibrium faster. But then we're at equilibrium and we stay there. So that was all LeChatelier's. It had to do with changing the concentration, either adding or removing, changing the temperature, either adding or removing, changing the pressure and changing the volume, and then the last would be adding a catalyst.